Hello, my name is Michael Wolf. My partner Andy Nguyen and I have prepared a final report on our flu data analysis. To quickly recap, the CDC has asked our assistance in forecasting the next flu season, which we've established as a horizon of 12 weeks. And for these purposes, we will supply a time series model using data collected from FluView, a weekly flu surveillance report collected from a number of laboratories run by the World Health Organization. In our EDA, we discovered that this data was non-stationary, exhibiting key seasonal components, which you can see in some of the plots that we have prepared. Please feel free to go back and review those at your leisure. We also did some initial analysis of univariate models, namely an ARMA 6.4 model, as well as an ARUMA model with a seasonality component. To close out our analysis on those, we performed Liang box tests as well as took a look at some of the residual plots to see if these models residuals exhibited white noise behavior, and we found in both cases that they do. Our Liang box test returned a p-value of roughly 0.9 for both of these, and when we examined the ACF plots as well as the residual plots, they do correspond with white noise behavior. If we were to recommend one of these models over the other, it would be the ARUMA model. Although this one doesn't perform as well from an ASE perspective, it does reflect the seasonal component of the data better when we look at rolling window ASE. However, we will want to keep both of these models in mind for ensembling. We also fit VAR models, again, sustaining the system frequency of 52. However, with one model exercise, we elected not to fit it to that frequency. Our AIC test selected P of 12 for both of these. Interestingly, when not fitted to the frequency, the ASE was significantly lower. We see this performance reflected in the forecast window. You can see the red line corresponds to the fitted model, and it's significantly overestimating the trend in this case. This is interesting behavior we see exhibited in this data that we'll want to review later. We also fit two different neural networks, a univariate neural network as well as a multivariate neural network, using all the variables as regressors. Using fivefold cross-validation, we found 5 nodes with UNN and 16 nodes with MNN. The MSE was lower for the MNN model. However, with ASE on the last 12 weeks of data, we did find that the UNN model did perform better. This can be seen in the forecast data with the UNN being represented by the red line. You can see it fits a lot better as compared to the blue line, which is our MNN. Finally, we fit 2 different ensemble models, a stationary model and a non-stationary ensemble. Our stationary ensemble is represented by our ARMA and VAR models, while our non-stationary ensemble is represented by our ARUMA and UNN models. Although the stationary ensemble performs better from an ASE perspective, we do see that the trend line appears to fit a little bit better in the non-stationary ensemble. Finally, for our selected model, we decide to go with the non-stationary ensemble. Although both the seasonal ARUMA model and the UNN tended to underperform from an ASE perspective, we do find that both of these fit the seasonal component of the data better. And when we actually go back and look at these using rolling window ASE, we do find that the rolling window tends to average a little better for both of these as compared to the stationary models. This would, of course, be expected, as a stationary model. A seasonal model would be better suited to fit the peaks and troughs that we saw in the realizations better than stationary models. We do see this represented quite well with our prediction intervals. In this forecast trend, you see those represented by the light blue lines around our trend line in blue here. They all around appear to fit the trend of the flu data quite well. So finally, some overall takeaways. Again, we did find that this came from a non-stationary process. This is expected given what we know about the flu in general. Although we did find that our stationary models were performing better with ASE. However, again, once we established the rolling window ASE, we were finding that our non-stationary models were performing better. We believe this is due to our stationary models having a tendency to regress towards the mean, which, as we already established, would be variant throughout the series. So we would, of course, expect rolling window to be a little more telling in these cases, and in that case, it did pick our seasonal models. One interesting observation, again, going back on those VAR models, we did find that the ASE was lowest when not fitting to the frequency of 52. We believe this may have something to do that we can't actually model some of the more annual trends. And so a good exercise in the future might be to try to look into a deterministic signal using sine or cosine functions to kind of model that period of 52 weeks rather than just a simple seasonal model. But thank you for your time. We look forward to the outcome.